let's run through a second graphing example. So let's start one where we have a polynomial that's been prefactored. So that should be helpful for a lot of our run through. This is a new one, right? We didn't work with this one yet. So brand new from scratch example. Let's go. No time to waste. So stage number one, let's check our end behavior. We said, right, we need our leading term, which is going to involve some unpacking here. So this would be a -3 from the -3 out in front, x squared from this x minus 2 squared, and then an x from here. So this is -3x cubed. So 3 and 3, our degree is 3, is odd. And then our leading coefficient is -3, which is clearly less than 0, negative number. So a negative leading coefficients and an odd degree, those things combined, and behavior does what? So if the degree is odd, it's mismatched. If the leading coefficient is negative, that means it's going to rise to the left and it's going to drop to the right. So rises left, falls to the right. So that's what we're going to expect from the edges of this graph as we move further out to the left and the right. That's the direction we're going to expect to head in. We'll see if how that fits together with all the rest of our information as we go. Step number 2, finding our x-intercepts, and let's figure out x-intercepts and touch versus cross. So this is prefactored, which makes finding our x-intercepts pretty fast. Minus 2 quantity squared, right? X plus 1. So the idea is to set this whole thing equal to 1. If this is prefactored, we can kind of jump right into the actual values, right? We don't need to spend a lot of time factoring. Again, that's what prefactored means. -3 out in front. -3 is never going to be 0, right? It's just a constant. There's no x value there, so we don't get any kind of intercept from that. X minus 2, quantity squared. This means x minus 2 times x minus 2. So this is two separate solutions. We're both going to get x equals +2. So we get x equals +2 showing up twice. So that's going to be multiplicity 2, which means that's going to be a touch-and term. So x equals 2 is going to be a touch-and term. That's our even multiplicity, right? Multiplicity 2. X plus 1 on the end equals 0. So that means the x itself must be -1. That's only showing up the once, so multiplicity is 1, which means that for us is going to be a cross. So two x-intercept values. This was degree 3, but only two x-intercepts. So one of them is a touch and turn, and one of them is going to be a cross. That is consistent. That all fits together, so that's fine. Moving right along. The y-intercept here, what's our original? So g of 0. So this is going to be -3 times, so 0 minus 2 quantity squared, times 0 plus 1. All this stuff is multiplied together. So this is -3 times -2 squared times 1. -2 squared is 4, so this is -3 times +4 is -12. So our y-intercept is going to happen at y is -12, so that's our coordinate, 0, -12. It's like kind of a medium-sized number, but again, we can kind of scale our graphs however we need to fit some of these points. So if we do get an intercept value that's a little bit bigger, that's fine. We can always sort of scale it accordingly. Next is our symmetry test. Symmetry question mark. So our original here, right? So g of x negative 3 times x minus 2 quantity squared times x plus 1. To a certain extent, we kind of know there's not going to be symmetry. I mean, assuming these x-intercepts are correct, they're not set up to be symmetric at all, really. If we start to expand this out, negative 3, this is going to be x squared minus 4x plus 4. If we multiply that out times an x plus 1, I want to move just a little bit faster. And so what I'm going to do is sort of spoil the ending here a little bit. In theory, you should kind of do a box multiply, expand this all out. You can kind of tell and expect. It seems like what's going to happen here is we're going to have both even and odd powers. And so this is not going to be g of x or negative g of x. What it looks like the results here are going to be is no symmetry. In theory, we should be, being a little bit kind of more, sort of run through those steps, maybe a little bit more definitively. But just to sort of speed the example up, I'm going to say it seems like that's not going to happen, and we'll sort of move along. Turning points. Question mark. Max turning points is going to be 2, right? So max turns is going to be 2. Our degree is 3, so at most, the maximum number of sort of turns we can take, what would be our potential kind of relative maximums and minimums, our peaks and valleys, is only going to be 2. So this is, one sort of smaller degree than our first example, but it has some different behaviors going on. Let's see if we can kind of put this all together on the graph. All right, our original up in the corner, so we said g of x, so negative 3 times x minus 2 squared times x plus 1. What do we need to be aware of? This looks like it's the middle. Again, we can kind of scale this however we want to. Whoop. That y-intercept value was down at negative 12, so we need to be a little bit aware of that scaling. That's really, in some sense, the only number we have to work with. That 0 minus 12. So what I'm going to say is maybe... maybe I'll sort of scale it so that each of these blocks is worth 3. So this is kind of a negative 3, this is a negative 6, this would be negative 9, and our negative 12 is going to be here. So that y-intercept, we'll sort of do our intercepts first. That is kind of a unique y-intercept. We said we have x-intercepts. Where were they? X was negative 1. And then x is positive 2. So I'm going to do, right, just sort of 1, 2, 3, 4, right? Negative 1, negative 2, negative 3. So I'm going to scale the x's to just be, 1 unit per block, but I'm scaling the y's to be a little bit of a bigger jump. So this is a little bit of a bigger stretch on the y values. That's, again, just to kind of make sure this fits nicely. We've got a lot of flexibility here in terms of what we can do. The end behavior, right? So we said we have a negative leading coefficient and we had an odd power. So that should be kind of rising to the left and falling to the right. What else did we say? Crosses and touches. X equals 2 is a touch. And x equals 1 is a cross. So, or I'm sorry, negative 1 is a cross. Let's do it from the left to the right this time. So our end behavior moving to the left, we should be sort of rising to the left, and then this is going to be a cross. So that means we're going through here. Maybe we should make this a little more steep because obviously we've got to connect down to this intercept. So this side of our graph, rising to the left, so shooting up and to the left. We've got to make it down to here. So this is pretty steep. And then in theory, we've got to make a turn to get back up to 2. Now 2 is another intercept, but 2 is just a touch point. So we're going to be coming up and then touching and turning down again. That fits because this is supposed to be headed down afterwards, right? Down and to the right. So then the only thing left is to just do a little bit of a connection here. The temptation is to sort of say that this -12 is like a minimum point. That's where the turn happens. I'm running into, honestly, my numbering here. My guess is this actually goes down a little further and then turns and comes back up. Again, we're not necessarily trying to draw this as the be-all end-all final version of this graph. We're trying to just get kind of a rough sketch of the behavior, the ups and the downs, where those turns might happen. And this fits it. So this has 2 turns, right? So that's consistent with what we were expecting, sort of a maximum of 2 turns. Turning points in the graphs. It's got the turn and touch, of course, here at x equals 2. This other intercept was a cross, and then we're sort of getting down to this y-intercept value here at -12. So that's our graph. That's -3 times quantity x minus 2 squared times quantity x plus 1. Pretty good. That's our graph. That is 3.2. We made it.